Welcome to Mechanical Engineering Made Simple. Right now, you are surrounded by this chaotic soup of physics that, honestly, by all rights, should probably tear the room you're sitting in to pieces.
Oh, absolutely.
I mean, if you were sitting in an office chair or driving on a highway or flying in a commercial jet going, 500 miles an hour, you are completely enveloped by these immense invisible forces: gravity, pressure, thermal expansion, constant vibration.
Yeah, the natural state of the physical world really isn't perfectly assembled, highly functional machines. Left to its own devices, nature prefers chaos, it prefers entropy. Yet the plane you are flying in doesn't just vibrate apart midair.
Right.
The suspension bridge actually holds the weight of thousands of cars, and your office chair doesn't suddenly collapse under you.
And that illusion of stillness is exactly what we are unpacking today. So this deep dive is your shortcut to understanding those invisible rules, the intense math, and the materials that hold our modern physical world together.
It really is a massive topic.
It is, and we've brought together a massive stack of sources for this. Authoritative texts like the Mechanical Engineer's Handbook, the Rules of Thumb for Mechanical Engineers, strict international standards for vibration analysis, NASA's Systems Engineering Guidelines, and even some industry career guides.
Quite the reading list.
Yeah, the mission here is to stitch all of this together so you can look at the built world around you and actually see the hidden mechanics keeping it intact.
It creates a fascinating perspective shift. When you look at any complex machine, after understanding these principles, you realize you are looking at a series of highly calculated compromises. A machine is essentially a negotiation between the laws of physics and human ingenuity.
Okay, let's unpack this.
Yeah.
Because the sources point heavily to NASA's definition of systems engineering, and they describe it as a holistic, integrative discipline.
Right. Holistic is the key word there.
Because you have structural engineers who want to make things strong, electrical engineers who want power, human factors engineers who want it to be usable. My immediate thought is systems engineering essentially like conducting an orchestra, where every material and component is a different instrument that has to play in tune?
That analogy holds up incredibly well, actually. If the brass section, let's say, the structural engineers, plays too loud, they might build a spacecraft that is virtually indestructible.
Which sounds good, right?
Right, but it will also be far too heavy to actually leave the atmosphere.
Aye.
NASA's guidelines explicitly mandate that systems engineering must balance these often opposed constraints so that no single discipline dominates the design.
So no one gets everything they want.
Exactly. The electrical engineers can't demand massive battery banks if it means sacrificing life support space. The entire machine has to be a coherent whole.
And reading through the handbooks, that negotiation starts at the microscopic level with the actual physical materials they choose. It's an intense screening process. They balance essential properties like tensile strength, how hard you can pull something before it breaks, with desirable properties, like how easy it is to manufacture, or simply how much it costs.
Because you might discover a material that has the absolute perfect strength-to-weight ratio for a jet engine turbine, but if it is astronomically expensive to mass produce or environmentally toxic, the engineers have to redesign the system or compromise on a different material.
Which happens all the time.
All the time. And we also have to remember we aren't just talking about raw steel and wood anymore. The handbooks highlight engineering thermoplastics, which are chemically formulated plastics designed to handle severe mechanical stress and huge temperature extremes while acting as semi-precision parts. We also see composites, materials made from two or more distinct substances, which used to be restricted strictly to aerospace. Today, those composites are functioning in everything from automobile brakes to microscopic biomedical devices.
But even with those advanced materials, the physics still finds a way to introduce absolute chaos. There's a concept detailed in the handbook called creep, C-R-E-E-P.
Ah, yes. Creep.
It sounds incredibly ominous, but it's defined as the ongoing slow deformation of a material under a continuous mechanical load. The text provided this example of a soldered joint in an aircraft. You have an electronics case sealed at sea level, but it operates up at 30,000 feet where the outside pressure drops and the internal pressure pushes outward.
Right, creating a constant stress.
Exactly, and if that mechanical load rests entirely on the solder eventually fails. Now, I struggled with this initially. Solder is a solid metal. How does a solid piece of metal slowly creep over time?
It goes against our basic intuition about how the physical world works, doesn't it? We tend to view metals as these static, permanent objects.
Yeah, exactly.
But materials are not perfectly static at the atomic level. A helpful way to visualize this is to think of a massive glacier.
A glacier, like solid ice.
Yes, solid ice. If you hit a glacier with a hammer, it chips because it is solid. But if you observe that massive sheet of ice over a decade, its own immense weight and continuous stress cause the crystalline structure to slip. It flows down the valley like a river.
Oh, wow. I've seen time lapses of that.
Right. And certain solid metals do the exact same thing under a sustained, continuous stress, especially when temperatures fluctuate. The atomic lattice literally slips and flows. It is a time-dependent deformation.
So the metal is flowing just on a timescale we can't easily see.
Exactly, which is why the handbook emphasizes that it is terrible design practice to place a soldered joint under sustained mechanical stress. If a seal utilizes adhesives, elastomers, or solder without actual structural metal framing supporting the load, failure isn't just possible, it is inevitable.
It's just a matter of time.
Yep. The solder will just keep creeping and stretching until the stress is relieved, which usually happens when the joint violently snaps. The structural framing has to take the load, not the sealant.
That transitions us perfectly into what happens when you take this perfectly balanced system built with materials that supposedly won't creep or melt and put it out into the real world. The environment immediately tries to bend or snap it. The texts break this down into 3 core concepts, which are force, stress, and strain.
Those are the foundational metrics for predicting failure. Force is the actual action trying to alter an object's state, which engineers measure in newtons.
Okay.
Stress is that external load divided by the specific area it is applied to. And strain is the physical result. It's the actual amount of deformation or stretching that happens to the material.
And the handbooks draw a very hard dividing line here between what is called the elastic region and yielding.
That dividing line dictates whether a machine lives or dies. A material operating safely in its elastic region, often called a hooking material, will deform when you apply stress. But the moment you remove that force, it snaps back precisely to its original shape.
Like a rubber band.
Or a diving board is a great example. It bends under your weight, but springs back perfectly when you jump.
But if you push that material too far, you cross the line into yielding. Yielding is unrecoverable. Plastic deformation. The metal bends and stays bent.
And in a precision machine, yielding is a catastrophic failure. A gear might not have snapped in two, but if the teeth have permanently yielded even a millimeter, they won't mesh anymore, and the machine basically tears itself apart.
I was reading about the sheer number of forces acting on a complex machine. Take an oil rig, for example. You have wind shear, ocean currents, the massive weight of the drill, thermal expansion from deep earth heat. I was trying to figure out how engineers calculate dozens of overlapping simultaneous forces without needing a supercomputer the size of a building.
They utilize the principle of superposition.
The text explained this, and honestly, it almost sounds too simple to be true.
It is an incredibly elegant mathematical workaround. The principle states that as long as the material stays safely in that elastic region we just talked about, the stresses from different loads can be calculated completely independently of one another.
Oh, really?
Yeah, you don't have to solve the whole chaotic storm of forces simultaneously. You calculate the wind load on its own, then you calculate the drill weight on its own, then you calculate the ocean current on its own. Once you have those individual numbers, you simply add them all together.
It takes an impossibly complex physics problem and breaks it down into elementary school addition.
Pretty much.
But even if the engineers keep all those combined forces well within the safe elastic region, there is a hidden mechanism that still causes things to break. Fatigue. The text uses a simple metal paperclip to explain fatigue, and it is brilliant. If you take a paperclip and just bend it back and forth 5 or 6 times, it snaps.
We've all done that.
Right. You didn't pull it apart with thousands of pounds of force. You just applied a very small load, repeatedly.
What's fascinating here is the sheer scale of fatigue-related problems. It's staggering. The engineering handbook notes that up to 90% of all design-related failures are due to fatigue. 90%.
Wait, why is it that high? If we have all this math to keep things in the elastic region, why is fatigue still destroying machines?
Because predicting static, stationary loads is relatively straightforward. Predicting how microscopic atomic bonds degrade over thousands or millions of dynamic cycles is incredibly complex. A fatigue failure is essentially a flaw created in the design stage, but it operates like a time bomb.
That's terrifying.
It is. The stress on an airplane wing might be way below the yielding point. But with every single takeoff and landing, every cycle, microscopic damage accumulates at the atomic level. Eventually, a microscopic crack forms, it propagates, and the part catastrophically fails while operating under totally normal conditions.
So we've talked about static stress and the repeated cycles of fatigue. But the sources point out another dynamic force that seems to be a mechanical system's absolute worst enemy. Uncontrolled shaking. We're talking about vibrations.
Vibrations are terrifying in an engineering context. A vibration can be harmonic, periodic, or completely random. The critical concept here is that every physical object in the universe has a natural frequency.
That's the frequency it naturally vibrates at if you strike it. Like tapping a crystal wine glass and hearing it ring at a specific pitch.
Exactly, that winging is the natural frequency. The danger arises when an external force, for instance, the spinning of a jet engine turbine, matches that system's natural frequency. That condition is called resonance.
And that's bad.
Very bad.
Yeah.
When resonance hits, the vibration amplitude increases massively. The machine effectively feeds on its own energy, and the shaking is limited only by the physical damping in the system. Resonance will literally tear a massive generator off its concrete mounts in seconds.
So what does this all mean? How do they stop a multi-million-dollar machine from shaking itself to death out in the real world?
Well, the industry relies heavily on strict international standards. The sources specifically detail the ISO 79189 and ISO 10816 series. These standards provide exact methodologies for measuring machinery vibration to catch subtle anomalies before resonance or fatigue destroys the equipment.
Reading through these standards, they are incredibly dense. There's a proposal by a Professor Kanke mentioned in the sources, an umbrella document that helps engineers figure out which standard they should even be using. It all comes down to evaluating the stiffness ratio.
Yes, the stiffness ratio is key.
It's the ratio of the pedestal's stiffness to the bearing stiffness. I was trying to visualize this, and I came up with an analogy. Tell me if this tracks. It's like a doctor deciding whether to check your pulse at your wrist or your neck, depending on your specific anatomy. You have to place your fingers where the signal is actually going to be clearest.
That translates perfectly. Let's look at a low stiffness ratio. This means you have very stiff bearings. Think of rolling element bearings, which are basically heavy-duty versions of the little steel balls inside a fidget spinner.
Okay, I can picture that.
Because those steel balls are stiff, they transfer the vibration energy directly through the bearing and into the machine's heavy outer casing. So, following ISO 10816, you put your sensors on the external pedestal or the casing to measure the shaking.
Because the signal is clearest on the outside.
Yes. But if the stiffness ratio is high, you might be using soft, fluid film bearings. In these, the heavy steel spinning shaft is literally surfing on a microscopic, highly pressurized cushion of oil.
Surfing on oil. Wow.
Because that oil cushion is soft, the heavy casing on the outside won't shake much at all. The oil absorbs it, but the shaft inside will be thrashing around violently. If you measure the casing, you'll think the machine is running perfectly. So you must use ISO 7919, which dictates measuring the internal shaft itself using proximity probes.
And once you take that measurement, the standards evaluate the severity using RMS velocity, sorting the machine into zones A through D. Zone A means you have a brand new, perfectly smooth machine. Zone D essentially means shut it down immediately before it explodes.
Exactly. And these ISO standards go far beyond bureaucratic red tape. They represent a hard-won global consensus. If a manufacturing plant in Germany builds a steam turbine for a power plant in Brazil, both entities must agree on what constitutes a safe vibration level. These standards facilitate international trade, standardize maintenance, and most importantly, keep people safe from catastrophic failures.
That covers measuring the machine once it's built. But you can't just build a $50 million jet engine, turn it on, and cross your fingers that you didn't accidentally hit the natural frequency. You have to predict the chaotic heat, the fluid flows, and the resonance before the metal is even poured. How do you do that?
That brings us to thermodynamics, fluid dynamics, and intense digital modeling.
Let's talk about the thermodynamics and fluid mechanics first. The text outlines the major cycles running our world, like the Brayton cycle. Instead of just listing the equation, the text explains the mechanism behind gas turbines and jet engines. It's essentially sucking air in, compressing it, igniting it to cause a massive expansion, and blowing it out the back to create thrust.
And you have fluid dynamics dictating how that air behaves. The Mach number is incredibly important here. At normal, everyday speeds, air flows smoothly around an object, but as you approach the speed of sound, as the Mach number increases, the inertial forces begin to overwhelm the elastic forces of the air.
What does that mean in practice?
The air actually compresses and starts acting almost like a solid spring. Predicting how heat and pressure behave in those extremes requires intense calculus.
Here's where it gets really interesting. How they actually solve that calculus for complex real-world shapes. An engine block or a curved turbine blade isn't a simple square or circle. The texts dive deep into FEM, the finite element method.
FEM is arguably the most important advancement in modern mechanical design.
The handbook describes it like examining a complex 3D puzzle. A computer takes an impossibly complex 3D shape, like a curved turbine blade, and breaks it down into millions of tiny, simple, symmetrical parts, little triangles or bricks called elements. These elements connect to each other at boundary points called nodes.
Right, creating a mesh.
Exactly. The concept is that if you know exactly how one single tiny puzzle piece handles stress, the computer can link millions of them together and predict how the entire massive structure will behave under pressure.
Instead of trying to write one impossible equation to solve the whole turbine blade, the software solves millions of simple equations simultaneously. To make it more accurate, engineers use a technique called H-convergence.
The text defined H-convergence as simply reducing the size of those individual elements. But why does making the puzzle pieces smaller make the math more accurate?
Think about laying a large, flat piece of wood over a bumpy road. The wood bridges the gaps, averaging out the surface. That is what a large element does in FEM. It calculates an average stress over a large area.
Okay, that makes sense.
But failure doesn't happen on average. It happens at microscopic, highly localized stress spikes, like a tiny sharp corner inside an engine mount. By making the elements smaller, you increase the resolution of the math. You stop averaging things out, and you converge on the true physical reality of the stress concentrations.
Now, I'm looking at the factor of safety section in the sources, and I have to push back on something here. Historically, if an engineer calculated a bridge needed to hold 10 tons, they built it to hold 40 tons, just to be safe. It was called overdesign.
Yes, the classic factor of safety.
Right. But now, the sources say FEM is so accurate that aerospace and automotive companies are stripping away that overdesign to save weight. If a computer tells us we can strip away 30% of the metal from an airplane wing to save fuel, doesn't that make the plane inherently more dangerous? What if the software's math is slightly wrong?
It is a valid concern, but it involves trading the safety of sheer bulk for the safety of precision knowledge. When we relied on massive factors of safety, we did it because we were largely blind to where the actual stress was flowing. We guessed, and we compensated with extra steel.
Better safe than sorry.
Exactly. But FEM removes the blindfold. We know exactly how the material will behave. By removing unnecessary mass, we significantly reduce the weight, which reduces the massive amount of fuel required, which lowers the overall kinetic energy the system has to manage.
So precision replaces the blunt instrument of overdesign.
Exactly.
But all of this supercomputer modeling and brilliant math means absolutely nothing without the human element. The sources emphasize the massive, highly skilled workforce required to actually design, build, and maintain these systems.
The logistics of maintaining the built world are staggering. The career guides from the sources use the natural gas and oil industry as a prime example, noting that it supports over 10.3 million jobs in the U.S. alone.
When people hear oil and gas, they often just picture roughnecks on a rig or petroleum engineers behind a desk. But the industry guide highlights bright outlook, craft trades, careers that are growing rapidly. We're talking about industrial machinery mechanics, heavy equipment mechanics, and electronics technicians.
Because the ultimate factor of safety isn't actually the FEM software or the ISO standard. It is human competence.
Right, because if a technician tightens a critical bolt 1 millimeter too far during routine maintenance, they introduce a microscopic stress fracture. All the brilliant supercomputer math is instantly ruined, and that fatigue time bomb starts ticking.
Exactly the point. The theoretical physics and the FEM models only keep us safe if they are translated perfectly into physical reality. When an industrial mechanic performs a rigorous 4-hour run-in test on a newly installed steam turbine, using proximity probes to measure the shaft vibrations, they are the ones actually hunting for resonance. They are verifying the thermodynamics. They ensure the machine stays within the elastic region.
To summarize our journey today, we started with a mandate that systems engineering is a negotiation between different disciplines to build a coherent whole. We zoomed in to watch the terrifying, glacier-like creeping of solid materials under continuous stress.
That was wild.
Yeah. We saw how the simple, repetitive stress of fatigue acts as a time bomb, causing 90% of all failures. We explored the stiffness ratio, using the pulse check analogy to decide where to measure the dangerous vibrations of resonance. And finally, we saw how finite element method software turns impossible engineering challenges into millions of solvable puzzles, though it all ultimately relies on the skilled mechanics turning the wrenches.
It's quite a journey.
It is. Thank you for coming along on this deep dive to become a little more well-informed about the hidden mechanics of the world around you.
I want to leave you with a final thought inspired by a core principle in the thermodynamics section, the conservation of energy. The rule states that energy is never created or lost, it only changes form. It becomes kinetic energy in a moving part, potential energy stored in a spring, or dissipative energy, which is energy lost to the environment as intense heat or sound.
Right.
The next time you are driving a car or flying in a plane, think about the immense shaking, the roaring noise, and the burning fuel. All of that is just part of a massive, perfectly orchestrated energy transfer. The engineers have somehow managed to tame that chaotic energy so it pushes you safely forward instead of tearing the metal apart.
It is wild to visualize. You're just sitting
Yeah.
there sipping coffee while thousands of pounds of explosive energy are being meticulously channeled through mathematically modeled metals right under your feet. So take a look around. Where else in your daily life are invisible, massive forces being perfectly balanced, just so you can go about your day without even noticing?